Thank you very much. It is truly a privilege and an honor to be here. So I also, even though it was forbidden on Saturday, will violate the prescription and thank the organizers very much for the opportunity to be here. So what I wish to do is talk a little bit about dynamical mean field theory and its combination with density functional theory and its use in studying real materials. The most important thing about this talk is that it's work done with Chris Marianetti, who is an outstanding colleague, assistant professor in the Department of Applied Mathematics at Columbia, Hyowon Park, a postdoc who came to us from the Rutgers group and has done spectacular things, and Hung Dang, who was a graduate student with me and is now at Jülich in Germany. All right, so look at, we know the reason why we're all here is that materials which contain electrons which are strongly correlated, which interact with each other strongly, do a wide variety of interesting things. We would be here all day if we discussed all of the things they do in detail, so I will just say that they produce phase diagrams with a large number of different bright colors on them. Right. Given this, what one would like to do after one has understood the basic origin and physics of these phases is two things to make them interesting and useful. One would like to be able to design materials which exhibit a particular desired behavior, and one would like to be able to control the behavior by appropriate application of external fields. And in particular, one of the things one would like to do is move the interesting behavior closer to, or indeed above, room temperature. I've put a red bar here indicating approximately where is room temperature, and many of the interesting phenomena happen at lower temperatures. If one could get them to happen at room temperature, or even outside temperature in New York City or Sherbrooke in the winter, one would be better off. So there is a potentially very promising direction for this, which goes by various names. The one I like at the moment is oxide epitaxy. The idea is that one can now combine interesting materials essentially on an atomic scale. So one can put together materials on a essentially layer by layer basis with different properties. Here are some pictures taken from a recent review article we did of work by Jack Jekalian and actually the Max Planck group around Bernard Keimer of superlattices composed of lanthanum, calcium, manganite, a colossal magnetoresistance material, and yttrium, barium, copper oxide. And the basic point of all this is simply that one is, from an experimental point of view, getting to the point where one can make one layer of one material, one layer of another, another layer of a third, and therefore one can control the chemical composition and structure, and therefore also other parameters including strain and local geometry to a much higher degree than one could previously. And this will give one, in principle at least, access to new physics. Here are two examples. One, which is solid, is a so-called multiferroicity. If you combine three different versions of these manganite materials, you can get something which has an electrical polarization. That's what's shown on this plot, plotted against temperature, which depends upon magnetic field. So you can get an electric polarization which depends on applied magnetic field, and also a spin polarization which depends on applied electric field. So this would be very interesting for technology if this temperature scale, instead of being 40 Kelvin, were 300 Kelvin. Another example, which has been reported in the literature but not reproduced by other groups as far as I know, is you can make a superlattice of lanthanum vanadate and strontium vanadate. These are materials neither of which is ferromagnetic in bulk, and the solid solution, lanthanum, strontium, vanadium oxide, is not ferromagnetic. But the report is that when you make this particular superlattice, you get a room temperature ferromagnet. So these black things are data at room temperature, and you see clearly a magnetization curve which says that it's ferromagnetic. So you get a new property not occurring in the bulk compounds, and which is potentially interesting. So this raises a severe challenge for theory. The best way to put it is what I think of as the Stewart-Parkin question. When I told Stewart-Parkin about this many years ago, he said, great, what do I have to put together to get a room temperature superconductor? And I think it's fair to say that we are not yet at the point, theoretically, of being able to give a crisp answer to that question. But it's a very reasonable question and an important goal for theory. More prosaically, you need theory to determine both electronic properties of model systems, so you know what kind of things you want to design into your material. You need to be able to predict structures, so you have some intuition for what kind of structures will actually form. And in particular, although I'm not going to talk about this very much, it's very hard to observe where oxygens are, and yet oxygen positions are crucial, and therefore theoretical insight into structural relaxations, and in particular what kind of distortions what kind of changes in the oxygen positions in these materials is very important to be able to predict. And finally, more generally, given this, you'd like to be able to connect the physical and chemical structure that you have to the properties that you want. All right. So that's a very ambitious task for theory, and I think it's fair to say that at the present state of the theoretical art, the best prospect for addressing these questions is this combination of density functional theory and dynamical mean field theory, to which much of this conference is dedicated. All right. So here I just want to give a couple of examples, which I will then come back to later in the talk, about how structure and properties are important for physics. This is old work by Antoine Georges and collaborators. If you look at D1 perovskites, for example, lanthanum titanium oxide, all right, it's crucial. The crystal structure plays a crucial role in the metal-insulator transition behavior. So as these people showed, if you take an lanthanum titanium oxide in a hypothetical ideal perovskite crystal structure, you will find that for any reasonable parameters, it's metallic, whereas if you study it in the so-called gadolinium ferrite distorted structure, in which the titanium oxygen octahedra are rotated in a particular pattern, then you get an insulator, as is observed. And the interesting contrast is this material strontium vanadate, which has essentially the same d-electron valence, but is in a cubic structure and remains metallic. So to understand the metal-insulator transition, you need to incorporate the physics of crystal structure, for example, on octahedral rotations on an equal footing with many body effects. A second thing, which I will come back to, is the rare earth nickelates, things like LaNiO3, yttrium NiO3, lutetium NiO3. These materials have a metal insulator and magnetic non-magnetic phase diagram, which is quite complicated. The lanthanum material simply remains metallic and non-magnetic down to lowest temperature. As you change the rare earth ion over to here, you discover a metal insulator transition which goes rapidly up to high temperatures. So all of this is insulating. The insulating behavior is intimately related to a distortion of the nickel-oxygen octahedra. Here are experimental data, and I'm embarrassed to say I didn't write down the reference. It's from the group of Alonso and Medard about a decade ago. And this is mean nickel-oxygen bond lengths. And what you see is that the metal insulator transition is associated with a disproportionation. So you start at high temperatures with the nickel-oxygen octahedra all having equal mean bond lengths. And below the transition temperature, what you discover is that one sublattice has short nickel-oxygen bonds, and the other one has long nickel-oxygen bonds. And it's this lattice distortion is intimately connected with the metal insulator transition. So to understand the metal insulator transition in this material, you need to incorporate the physics of changes in the transition metal-oxygen bond length on an equal footing with many body effects. All right. Another example where you need to relate structure and physics to properties is charge transfer. Here is a paper, one of many examples. I pulled it essentially at random, showing that if you take a interface between two materials, calcium ruthenate, which is a paramagnetic metal, and calcium manganite, which is an antiferromagnetic insulator, this interface is ferromagnetic. You see here measurements of the magnetic moment per interface layer. The reason that this happens is that some amount of charge flows from one of these materials to the other and effectively dopes the near interface layers of the calcium ruthenate, and that doping converts the antiferromagnet to a ferromagnet. So charge flows across the interface and changes the properties in a crucial way. So if you think about this, several questions naturally arise, of which the most important is, if you have an interface, how much charge flows and in what direction? Right? So to understand superlattices, you need to understand charge flow between different materials. That means that on an equal footing with many body physics and energetics, you need to understand differences of work functions, atomic physics contributions to electronegativity, and the charge balance issues associated just with the usual Coulomb interaction. Right? So you need to put all these things together if you wish to understand the physics of these materials. And to repeat what I said before, basically, the theoretical technique that we have in our hands at the moment, which will allow one to address that, is this combination of density functional theory plus dynamical mean field theory with full charge self-consistency. Okay, now, there's an important point here, which is worth stressing. This business of structural distortions at interfaces and charge flow in interfaces is intimately related to the many-body physics of the metal-insulator transition. I already described how local structure is crucial for the metal-insulator transition. The relation to charge flow arises from classic work in our field by Zanin, Zawadzki, and Allen. This is the reference. It's now 20-something, 30-year-old physical review letter. What they observed is that if you consider the general family of transition metal oxides, there are two important parameters which govern the physics. One is an on-site interaction on the transition metal site, U basically, and this T, by the way, is some measure of bandwidth, not temperature. The other is the PD, the difference in energy between the D level and the P level. And so they distinguish two regions, the so-called Mott insulator region, where the PD splitting is very large and you can only focus on the D levels, and the charge transfer insulator region, where the physics is controlled by the PD splitting and not by the interaction strength. All right. And actually, this got somehow out of order. Oh, I see. Yeah, interesting. All right. So let me show you this, which is slightly out of sequence, but is a simple calculation that we did with another postdoc at Columbia, Hanghui Chen, which is published here, which investigates charge transfer in a superlattice composed of lanthanum titanate and lanthanum nickelate. Right? Now, lanthanum titanate, as I described, is a so-called D1 Mott insulator. Lanthanum nickelate is a correlated metal, as I described, with no particular order. All right? And the question is, what happens if we put these two things together? Here's a cartoon. You have lanthanum titanate, which has oxygen P and titanium D levels, and a little Mott gap and a Fermi level here. Lanthanum nickelate, which has oxygen P levels in which the nickel and nickel D levels very close, and you have a metal. So if the P levels basically line up, then you would say the titanium D levels lie higher than the nickel D levels. In other words, the nickel is more electronegative than the titanium. And therefore, you might expect charge to flow from here to here. If all the charge flows, then you may get an insulator. You will fill up this band, empty out this band, and get a different kind of insulator. You will go, in simple cartoon language, from D1, D7 to D0, D8. So that's a pretty cartoon. You may ask if it happens. We did a calculation using the density functional plus U method, which is just density functional plus dynamical mean field theory, but solving the dynamical mean field equations by a Hartree approximation. And this rather complicated figure explains what we found. So start here. This is density functional plus U for lanthanum nickelate. For the aficionados, this is the paramagnetic solution, so we don't have a Mott gap. Here you see the oxygen band. Here you see the titanium D band. This thing is the Fermi level. Again, if you did a proper treatment of the correlations, you would get a little gap here. Here is lanthanum nickelate. You see oxygen P, strongly hybridized with nickel D, a Fermi level here, so it's a metal. Now, you put them together into a superlattice, and what you see is a small gap, titanium D empty, nickel D completely filled. So the way this works is that the P states here approximately line up, and you get the propensity to charge transfer by comparing the PD gap here to the PD gap here. So to understand charge transfer in superlattices, the simple rule of thumb you should have is that the oxygen bands approximately line up. That's here. This is just what I showed you before. And the energetics driving charge transfer is then the difference of D levels, which are tied approximately to where the oxygen P level is. So therefore, understanding the PD splitting in the material is crucial for the metal-insulator transition. Zanen, Zawadzki, and Allen taught us that 30 years ago. And it's also crucial for understanding charge flow across superlattices. Now, this is, of course, a slight cartoon. These things, if you go back and study these calculations carefully, you will discover that they don't line up exactly. There's a sort of half a volt mismatch. But the rough physical picture is what I said. OK, so now I should like to ask, excuse me, are these estimates correct? So I would now like to look, all right, at two examples of these materials. And before doing that, and I realize that I timed this talk incorrectly, I'm just going to make your eyes hurt by skipping backwards here to explain to you briefly how my view of this density functional plus dynamical mean field theory stuff. So there's a general approach to many-body electronic structure, which is you take your entire degrees of freedom and you partition them into a correlated subspace, which you treat by a more exact method, and a background, which you treat by a more or less mean field method. And then you have to embed the correlated subspace in your broader electronic structure. All right, so the correlated subspace is the transition metal d orbitals. You have some interactions amongst them, which you have to discuss. And then you do a calculation which provides a self-energy which lives on the d levels and corrects your mean field electronic structure. So you start with a bare electronic structure which defines a p and a bare d level energy and a d orbital wave function. That gives you something like what I showed here. You have a self-energy which lives on the d site and which encodes the many-body physics. And there's one very important point of this that I want to stress. This self-energy, of course, is a dynamical quantity. It has both real and imaginary parts. And as you can see, this is a calculation actually for lanthanum nickelate as a function of lattice distortion. The self-energy has a large real part. I don't know how easy it is to see, but this is 6 electron volts, 5 electron volts, 4 electron volts. So over the whole interesting frequency range, there's structure as a function of frequency. But there's a basic average value, which is not small. So that acts to shift the d level very substantially from where your band theory put it. And that's why, in this theory, you also need what's written in blue here, the so-called double counting correction, whose job is to cancel off some or all of that Hartree correction and put the d level back where it's supposed to be. All right. So the crucial question for all of this physics is, what is the double counting? Now, there is an accepted choice in the literature which goes by the acronym FLL, which I don't want to explain. But the gist is that you take your interaction and more or less you just take its average expectation value. That's written here. And that gives you a double counting energy. And from that, you can get this double counting correction. If you're interested, it's discussed in more detail here. One thing I want to stress for later use, this is an interaction energy, right? An interaction energy counts each pair. So if you sum over all states, you have a half here. All right, and don't forget that half. All right. So now, with that, let me go back to these two examples just of bulk materials. All right? So we do the density functional plus dynamical mean field theory plus full charge self-consistency plus FLL double counting for different values of the basic interaction energy. The J is actually 1 eV. This is density functional theory for a rock salt nickel oxide. These are calculations for different U values. And what you see is you get an insulator. There's a gap at the Fermi level. And interestingly, you see that red is the oxygens, that independent of where you put the U, the basic gap between the highest oxygen state, highest occupied oxygen state, and the lowest unoccupied transition metal state is essentially the same, independent of U. This combination of full charge self-consistency and the FLL double counting correction, what it does is, independent of the interaction that you assume, it keeps the PD splitting at essentially a constant value. Now, this constant value is, in fact, a little bit too small. The P levels are a little bit too close to the D levels, and the insulating gap is a little smaller than is observed. You can see that here. This is just a comparison to data. You can do the same thing for lanthanum titanate, also known to be an insulator, or yttrium titanate. And what you discover is you always get a metal. It puts the P levels so close to the D levels that you don't get an insulator at all. All right. So what's going on here? All right. There's a very instructive example, which is strontium vanadate, which is a cubic moderately correlated metal. We do exactly the same procedure. This is density functional theory. This is the analog for this strontium vanadate material for what I showed you with the nickelates. You see that, again, as you change the interaction, it wants to keep all the states in approximately the same position. Now here, this is the calculated oxygen states. What I show in blue here is the experimentally measured from photoemission oxygen bands. So what you see is that the theory puts the oxygen bands, essentially independent of the interaction energy, puts the oxygen bands about a volt closer to the Fermi level than apparently they really are in real life. Right? So what that means, if you go back to the Zanen-Zawadzki-Allen phase diagram, is that as you turn on interactions, what this DFT plus DMFT theory is doing is saying, with full charge self-consistency, is saying that the material follows approximately this trajectory, keeping the renormalized PD splitting essentially the same independent of U. And for many of the materials, such as lanthanum titanate, yttrium titanate, lanthanum vanadate, sitting on the metallic side of the phase boundary. So that's what the theory does. All right. Now, you may ask, what's gone wrong? And a first thing you can do is ignore this theoretical double counting correction and just adjust the double counting correction by hand. So here we did a toy calculation where we took lanthanum titanate, again in the experimental gadolinium ferrite distorted structure. And for each value of U, we adjusted the double counting correction, that is to say the physical EP minus ED, in such a way as to get the insulating gap approximately correct. And we also did it for lanthanum vanadate. All right? And then we asked, where did the oxygen bands wind up? In this case, with a small value of U, the calculated oxygen bands are off the screen here at a very low energy. For very large U, the calculated oxygen bands are close to the Fermi level. For an intermediate U, they're fairly close to where the experiment is. So what I take away from this is that the problem with this theory is the double counting correction, or the position of the oxygen bands. Right? And that if you have a reasonable U interaction, you will reproduce the experimental behavior, provided that you adjust the double counting correction appropriately. All right. By the way, this is just a brief aside. The gadolinium ferrite distorted structure is essential to get an insulator. If we take the cubic structure, we just can't make this work for any reasonable parameters. Okay. So how do you position the oxygen levels, given that the existing theory doesn't work? Given that the fully charged self-consistent DFT plus DMFT pins the PD splitting to a value which is fixed independent of U, slightly smaller than DFT, fixed relative to DFT, and too small relative to experiment. So there's two ways to think about this, and I think that at this stage we don't know which is the right one. One option is to modify the band theory to say that this fully charged self-consistent process, what it does mathematically is keep the physical P levels a constant distance from the underlying band theory where you started. So you might say, well, we should have a better band theory than DFT that would put the bare oxygen levels a little farther down to start with. Then, because the theory keeps your physical P levels at a fixed distance from your starting one, if you start with an oxygen which is lower down, you will then have a correct result. Right? And it's not unreasonable. After all, density functional theory is a ground state theory. there's no reason why it should get excitation energies like the position of the oxygen band right. It may be that something like GW is a better starting point than density functional theory. So that's this. The alternative, as I showed you in the previous toy calculations, is to modify the double counting correction. Right? And there are two recent papers which have done this, following our paper which pointed out this problem. One is by the Rutgers group, and what they say is that you should modify the double counting correction so the double counting energy is the occupancy of the D state times basically your interaction, times not the occupancy of the D state, but something to do with the formal valence. That's why I put n naught here. This is just a fixed number, whereas this is an operator. So they show in their paper that if you then take this U equals 10 eV, you can get a quite consistent description of a whole range of properties and a whole range of compounds. Right. Now, to my mind, there's a big problem with this, which comes back to this factor of a half, which I showed you before. We need to use this theory to get energies right if we want to be able to discuss what is the correct structure. And because this thing is not an interaction, it's just a bare level shift, this term in the energy doesn't come with a half. So there's an enormous difference in energy between this and this. And to my mind, that's a fundamental problem with this. All right. Now, there's an alternative ad hoc approximation, which Hyowon Park suggested. And we have used it in this paper, which I'm going to explain for a minute, and it looks like I'm going to run over by 1 or 2 minutes. So take the standard double counting form, and instead of using the interaction U, which you would normally have, use a different value, U prime. If you make this U prime less than U, then the double counting shift is a little smaller than the Hartree shift you started with. So it has the effect of increasing the PD splitting. But it's also good because it's an interaction. So in particular, it has this key factor of a half. All right. So we did this, and there's a separate talk which I'm not going to give you, which is a great achievement, I think, of Hyowon. He has made an efficient working implementation of calculating total energies within this DFT+DMFT procedure. All right. And we have used it to investigate this nickelate phase diagram. So we have studied the dependence of the energy on this lattice disproportionation. All right. And here's what we find. Look at the right-hand side first. We considered lanthanum nickelate. We consider energy as a function of distortion. And this distortion is something which interpolates between the observed high-temperature structure and the hypothetical distorted structure down here. So we just linearly interpolate. We ask for the energy. And what you see is that for the DFT+DMFT, that is the black and blue curves, for lanthanum nickelate, it doesn't want to distort at all. Right? So that's in agreement with experiment here. If you do DFT+U for what it's worth, it does weakly want to distort. These things are weakly negative. Right? Now you go over to this end member, which has a very strong distortion. All right? If you do DFT+DMFT with the standard double counting, that is keeping U prime equals U, that's the black one, you discover that it does not want to distort. If you do the same calculation using a U prime which is slightly less, 4% less, 4.8 eV, you discover that it wants to distort with a distortion which is of approximately the correct magnitude. Again, as you would expect, if you do DFT+U, you get a much stronger distortion. All right. Now, I don't have a figure to show you, but this small change in U prime also has the effect of putting the PD splitting to approximately the correct value. Again, if you do standard DFT+DMFT, the P levels are too close to the D levels. You make this change, 0.2 times the D occupancy of 8, it shifts the P levels by about a volt and puts them in approximately the right place. So this is admittedly ad hoc, but it shows you that getting the double counting correction and the PD splitting right is crucial for the energetics. All right. So once you make that choice, you say that you take this U prime is 0.96 of U. You can then, in fact, reproduce the entire pressure unit cell volume phase diagram of the nickelates across the entire series of rare earth ions. So that red and blue are where we find the structural and metal insulator transition. The green shaded region is experimentally where the system is insulating. And you can see that this just works. You can also see, this is a side point, again, not unsurprisingly, that if you do DFT+U, which is a Hartree approximation, it grossly overestimates the tendency to order. All right. So I think then that I'm slightly over time. I'm sorry about that, and I'm done. The key thing that you should take away from this is that the key issue for density functional plus dynamical mean field theory, which we have to resolve if we're going to get all this superlattice stuff straight, is the proper PD energy splitting. All right? And the question I would like to leave you with is this a problem of the double counting correction, or is this a problem of the underlying band theory on which you base this? So thank you very much for your attention, and I'll stop here.
Yeah. Thank you. We have some time for questions.
Nice Silke in the back.
Yeah.
Instead of using this U prime and all that, why not use a UPD?
Ah, good question. That's a possibility. Basically, there's a very practical reason, which is that we haven't yet implemented total energies for a model with UPD. And indeed, it comes back to a problem with dynamical mean field theory. We don't have a good dynamical treatment within this formalism of the VPD. So VPD has the effect, clearly, of making a Hartree shift in the PD energy splitting. But meshing that correctly with a total energy is, at least this is a problem that we haven't solved yet. I would also add that the double counting issue becomes severe because a lot of the VPD is on some level in the band theory. So my view is that the right way to do this would be to build this all on GW. But we haven't done that yet.
Thanks, Andy. Very nice talk. Actually, I would like to continue on Tanushri's question. So UPD is one question, and as you mentioned, GW corrections, exchange energies, exchange shifts, another one. And
yes.
Would you agree with the following statement? On conceptual grounds, you would expect that at least a large chunk of this wrong energetic distance should be due to this. Because if you take materials which do not have d electrons, so in my talk I cited strontium titanate, everybody would agree immediately that the PD gap is wrong,
yep.
Well, and that the issue is here something that you should actually do with a screen GW.
Yeah, well, yes, I would agree with that statement. I would put it slightly differently. I mean, we know, and I didn't have time and space to put it in this talk, that DFT in all its incarnations has troubles with excited states. It doesn't get them correct. And this energy mismatch of about a volt is well within the reasonable range of DFT thing. So you have to fix it up somehow. And the question is, what's the right way to do it? And I agree that GW is maybe a promising way to think about it. My colleague Marianetti says that this that the right way to fix it up is this double counting correction, because all you really care about is a relative splitting between two bands. Maybe it's theological, maybe not. I think that's an issue where we have to do more.
Andy,
yeah.
Fantastic agreement that you get with this U prime is equal to 0.96 U, and if you have to believe that, then I guess this 0.96 has some deeper physical meaning. And would you like to speculate what the deeper meaning is?
No. Basically, my belief is that, and I don't have the relevant figure, I'm embarrassed to say, in my computer. But the 0.96 is a little bit of a fake, because right. These are all d electron calculations. So there's a large ND floating around here. So how big this shift is depends on how many d electrons you include in here. Right? It's basically a Hartree shift which has to do with the interaction with all the other electrons. So what this is doing operationally is pushing the d levels up relative to the p levels by about a volt. That's the meaning of this 0.96. And if you did a theory where you only included the EG levels, so there's a smaller ND, then you would need a different U prime to push those levels which you care about up by the same amount. But the deeper meaning is really it's just putting the p levels in the right place.
Just a quick question together with that. The ND,
yeah.
How do you evaluate that?
Oh, well, this is a theoretical calculation, right?
Yeah,
if
sure.
If you're doing
even then,
yeah, but so within the theory, for any of this to make sense, you need to be able to evaluate ND, right? You have to have a definition
That's
of the
right.
D level
So
so you can
what-
put correlation.
exactly.
So operationally, what we do is maximally localized Wannier function, just Marzari-Vanderbilt maximally localized Wannier function with an energy range which is the entire PD manifold.
okay.
So that's what we mean by the d orbital, is the thing which comes out of that process.
Yeah, so, I mean, going on in the same line as everyone has been talking about. The thing is, we've done some recent work on some early transition metal oxides. And I think it's this effect should be coming from the U on the oxygens. Because when you talk about a large U, you take a PD model, everyone talks about a large U on the transition metal site, which is something like 7 to 10 eV.
Yeah.
In that same model, you evaluate the U on the oxygens, it's about 7 eV.
Yeah.
So, I
Right.
mean...
No, there's a substantial, and again, the question is how much of that does DFT get right? Right, there's clearly...
No, I mean, this is from constrained RPA.
No, but wait. But I would agree that there's a large U on the oxygen. And furthermore, in these kind of theories, even in the nickelates, which have an enormous amount of covalency, relatively speaking, the hole density on the oxygen is very small, right? You transfer approximately 1 electron from the oxygen to the D level. The nickel is D8, not D7. You have 3 oxygens per nickel. That means it's a third of an electron per oxygen, really. So the oxygen bands are still almost full. So almost the entire effect of the U on the oxygen is a Hartree effect. There's essentially no dynamical effect, right? And the question is how much of that Hartree effect is already living in your underlying DFT calculations, which do, after all, have some measure of the interaction, and how much is not. It's clear that there is a big Hartree effect. As I say, what's not clear to me is how much is already living in the DFT.
But maybe one needs the DFT doesn't have a orbital dependence, which you bring in with a plus U treatment. So maybe that's the...
Yeah, that's possible. Actually, that's interesting to discuss, yeah.
I just have a very technical question, actually. So I think one of the reasons why the group of Rutgers is using ND0 as well is that they want to work at constant correlation. So when you do the self-consistency over the charge, they would use the same double counting. I just wondered if here ND was updated at every iteration, or is it here as well? And there is no stability issues at all. So
I mean, statement 1, the way we do it is that you do your DFT, you do your double counting correction, you do your DMFT, then you take that, then from that solution, you re-update the D density matrix and then re-update the cone-sham potential, and then iterate in that way. So that's what was done. And at least for the cases that we considered, which are titanates, vanidates, chromates, where we use the TRIX code, and the nickelates with the total energy calculation, where we used stuff that Hyowon more or less inherited from his time at Rutgers, and which we've modified in various ways. We didn't encounter any terrible instabilities. But I would say that the success of the Rutgers group just on the phenomenological level is very impressive. Again, the thing that bothers me is that it's not an interaction energy. So in my view, you're going to have big troubles once you start trying to optimize structures.
Yeah, I think we are running now late. We'll probably not take any more questions. I just wanted to make a very quick comment that I like the idea that this double counting is taken care by less value of U, because in that case, there are many other theories which can work better, particularly many body theories which do not like the strong U because of convergence problems. So I think I just like that idea. Thank you very much again.